Imagine standing on nothing, not on rock, not on soil, not on sand, on nothing solid at all. Imagine that beneath your feet there is only water, dark, warm, endless water stretching in every direction to a horizon that has no edge, no shore, no interruption of any kind, just ocean, just the slow, patient rise and fall of swells that have been rolling since before there was anything alive to notice them. The sky above you is not blue. It is a pale, hazy orange, the colour of a sunset that never ends, and through it the sun hangs, smaller and whiter than you know it, dimmer as if seen through frosted glass. There is no land, there is no continent, there is no island, there is nothing but the water, the sky, and the faint mineral smell of a young ocean that is still warm from the heat of its own making. This is Earth. Not the Earth you know, not the Earth of mountains and meadows and coastlines drawn on maps, but an earlier Earth, a simpler Earth. A planet that spent the first 3 billion years of its existence as a single, unbroken sphere of water, a water world, a marble of dark ocean hanging in space, with no land anywhere on its surface, no footprint possible, no place to stand. For longer than the age of every fossil ever found, for longer than the entire history of complex life, for longer than the time between the first fish and you, this planet had no continents at all, just the ocean, just the rain, just the slow, deep patience of geology, working in the dark, building something that would not appear on the surface for billions of years. Tonight, you're going to drift across that ocean. You're going to start at the very beginning, when Earth itself was still molten, still glowing, still so hot that the sky was made of rock vapour and the surface was a sea of liquid stone. You're going to watch the first rainfall. You're going to float on the first ocean. You're going to sink slowly, gently, to the floor of that ocean and see the places where life first flickered into existence, in the warm dark water near cracks in the planet's skin. And then, over the course of billions of years compressed into a single quiet evening, you are going to watch the continents appear, not crashing up out of the waves like whales breaching, but slowly, silently, grain by grain, as the planet's interior sorted itself into layers and pushed the lightest rock upward, the way cream rises to the surface of milk that has been left to stand. There is nothing to hurry toward. 3 billion years is a long time, and we have all night. Settle yourself. Let your breathing slow. Let your weight sink into whatever is holding you. The ocean is patient. The story is patient. And the continents, when they come, will come so slowly that you might not even notice, which is in a way exactly how it happened. Here is where it starts. 4.5 billion years ago, give or take a few tens of millions of years, Earth did not exist. The space where it would be was occupied by a disk of gas and dust and tiny fragments of rock, all slowly orbiting a young star that had only recently ignited. The disk was vast, stretching from the inner reaches where Mercury now orbits to the outer darkness beyond Neptune, and it was hot and chaotic and full of collisions. Grains of dust stuck to other grains, pebbles stuck to pebbles, rocks stuck to rocks, and over the course of perhaps 10 million years, a span of time that seems enormous to us but is barely a blink in the life of a star, those collisions built up larger and larger bodies until the inner solar system was dominated by a handful of rocky protoplanets, each one the size of the Moon or Mars, each one still growing, each one still being struck by smaller bodies at tremendous speed. Earth formed from those collisions, not in a single moment, but in a long, violent crescendo of impacts, each one adding mass, each one adding heat. By the time the process was mostly finished, the young Earth was a sphere of molten rock roughly the size it is today, glowing dull red and orange in the darkness of space, its surface a churning ocean of liquid magma, its atmosphere a choking blanket of steam and carbon dioxide and vaporized rock. There was no water on the surface. There could not be. The surface temperature was above 1,000 degrees. Any water that existed was trapped in the atmosphere as superheated steam, or locked inside the minerals of the molten rock itself, waiting. And hanging in the sky above this glowing world, so close that it filled a quarter of the visible heavens, was the moon. Not the small, pale, distant moon you know. This moon was enormous. It had formed only recently, perhaps 50 million years after Earth itself, in a collision so vast that it is difficult to imagine. A body the size of Mars, a protoplanet that scientists have named Theia, struck the young Earth at a shallow angle, at a speed of perhaps 40,000 kilometers per hour. The impact liquefied both bodies. It blasted a cloud of molten rock into orbit around the wounded Earth, and from that cloud, over the course of perhaps a century, the Moon accreted, pulling itself together from a ring of glowing debris, cooling, solidifying, settling into an orbit so close that the tides it raised on Earth's magma ocean were hundreds of meters high. The Moon and the Earth were born together, in fire, in violence, in a collision that reshaped the inner solar system, and for the first few 100 million years they hung close to each other in the dark, the Moon slowly spiralling outward, the Earth slowly cooling, both of them waiting for what would come next. The Moon's influence on the young Earth was extraordinary, and it is worth pausing here to let the strangeness of it settle. Today, the Moon raises tides of perhaps a metre or two in the open ocean, the gentle rise and fall that you notice if you spend a day at the beach. But when the Moon was 20 times closer, the tidal forces were not 20 times stronger. They were thousands of times stronger. The magma ocean on Earth's surface was pulled into enormous bulges, tidal waves of liquid rock, hundreds of meters high, that swept across the surface every few hours. The day was only 6 hours long, because the Earth was spinning much faster than it does today, and the Moon completed an orbit in less than a day. The sky was a blur of motion. The enormous Moon rising and setting and rising again, the stars wheeling overhead at a pace that would make you dizzy if you could stand to watch. The magma tides surging and retreating with a rhythm that was fast and violent, and utterly unlike the slow, gentle tides of the modern ocean. But the Moon was also slowing the Earth down. The tidal friction, the drag of those enormous bulges of rock being pulled across the surface, was transferring energy from Earth's rotation to the Moon's orbit. The Earth spun slower. The Moon moved further away, and with each passing million years the day grew a little longer, the tides grew a little smaller, the Moon grew a little more distant in the sky. It was a slow dance, a waltz between two bodies that had been forged in the same catastrophe and were now, patiently, finding their separate rhythms. The dance is still happening. The Moon is still moving away from the Earth, at a rate of about 3.8 centimeters per year, roughly the speed at which your fingernails grow. In 1 billion years it will be noticeably further away. In 10 billion years it will be so far that a total solar eclipse will no longer be possible. But tonight, in this story, it is still close. It is still enormous, and it fills the Hadean sky like a lantern held too near. Let the image of that enormous Moon rest at the edge of your awareness. You do not need to hold it clearly. Just let it glow, pale and close, somewhere above you, while the world beneath it cools. Close your eyes for a moment if they are not already closed. Picture the surface of the Hadean Earth. That is what geologists call this era. The Hadean, after Hades, the Greek underworld. It is an appropriate name. The surface is a lake of fire. Glowing orange magma stretches to the horizon in every direction, broken by darker rafts of cooling basalt that form and crack and sink and reform, like ice on a river in early spring, except that the river is made of liquid rock, and the temperature is 1200 degrees. The sky is dark, not black, but a deep bruised orange-brown, lit from below by the glow of the surface, and from above by the constant flash of meteorite impacts, each one a streak of white light followed by a bloom of molten ejecta. The air, if you could call it air, is a thick soup of water vapour, carbon dioxide, nitrogen, and trace amounts of gases that would kill any living thing instantly. There is no oxygen, there is no ozone layer. The ultraviolet light from the young sun falls directly onto the surface, unfiltered, intense enough to break apart complex molecules in seconds, and yet. This is the planet that will, in time, become everything you know. Every mountain, every river, every forest, every ocean trench, every grain of sand on every beach, all of it is here, in this lake of fire, waiting to be sorted, cooled, separated, and assembled. The iron that will form Earth's core is already sinking toward the centre, a slow catastrophe of dense metal falling through lighter rock, releasing heat as it goes, heat that will keep the planet's interior molten for billions of years. The silicon and oxygen and aluminium that will form the continents are already present, mixed into the magma like ingredients in a batter that has not yet been baked. Everything is here. nothing is ready. The recipe has been assembled, but the oven has not yet cooled enough for the cake to set. Let that image rest. Let the heat of it settle against your skin, not as a burn, but as a warmth, the way a sunlit wall feels hours after the sun has gone down. The Hadean Earth is warm. It is the warmest this planet will ever be. And the warmth is patient. It has nowhere to go but up, into space, slowly, degree by degree, century by century, as the surface radiates its heat into the cold vacuum above it. Now, let us watch what happens when the heat begins to leave. The cooling of the Earth is not a simple process. It is not like watching a pot of soup cool on a counter. It is more like watching a pot of soup cool on a counter while someone keeps adding heat from below, because that is exactly what is happening. The radioactive decay of elements deep inside the Earth, uranium, thorium, potassium, is generating heat constantly, and will continue to do so for billions of years. The planet is not simply losing heat. It is losing heat from the top while generating heat from the bottom, and the balance between those two processes determines everything about what happens next. For the first few 100 million years, the top wins. The surface cools. The magma ocean begins to solidify, not all at once, but in patches. Dark rafts of basalt forming on the surface like skin on hot milk, cracking apart, sinking, reforming, cracking again. The process is agonizingly slow by human standards, but extraordinarily fast by geological ones. Within perhaps 200 million years of the moon-forming impact, by about 4.4 billion years ago, the surface has cooled enough that something remarkable can happen. Something that will change the planet forever. It begins to rain. Not the kind of rain you know, not a shower, not a storm, not even a monsoon. This is a rain that has no name in any human language, because no human language was designed to describe a rain that lasts for millions of years. The atmosphere of the early Earth contains an almost unimaginable amount of water vapor, the equivalent of all the water in all the oceans today, suspended as steam in a sky that is hundreds of kilometers thick with cloud. As the surface cools below the boiling point of water, which at the atmospheric pressures of the early Earth is well above 100 degrees, that steam begins to condense, and when it condenses, it falls. Imagine the sound. You do not need to imagine the sound clearly, just let the idea of it rest at the edge of your hearing. A rain falling onto hot basalt, the hiss of water turning to steam on contact, then the steam rising, cooling, condensing, falling again. The cycle repeating over and over in a rhythm that has no beginning and no end. The first drops evaporate before they reach the ground. Then the ground cools a little more, and the drops reach the surface and skitter across the hot rock like water on a griddle. Then the ground cools a little more, and the drops begin to pool, small pools in crater basins, shallow lakes in the low places between volcanic ridges. The pools grow, the lakes connect, the water rises, and still the rain falls, year after year, century after century, millennium after millennium, filling the low places of the planet with an ocean that will not stop growing until there is no more water left in the sky to fall. Take a slow breath. Let it out. Listen to the rain, if you can. Not the real rain outside your window, but the ancient rain. The first rain. The rain that built the ocean. It is the oldest sound in the world. Older than thunder. Older than the wind. Older than the cry of any living thing. Just water falling on stone over and over, patient and purposeless, filling the world. By about 4.3 billion years ago, the rain has mostly stopped. Not because the clouds have run dry. They have, but because there is nothing left to fill. The entire surface of the Earth is covered in water. Not a shallow puddle, but a true ocean, perhaps 2 to 3 kilometers deep in most places, far deeper in the great basins left by ancient impacts. The water is warm, 70, 80 degrees Celsius, and it is not the clear blue water of a tropical lagoon. It is dark. It is slightly green, tinged by the dissolved iron and other minerals that have leached from the basalt seafloor. It smells of sulfur and hot metal, and something older than either, the mineral tang of a planet that is still exhaling the gases of its own creation. And there is no land, nowhere, not a single island, not a single reef, not a single sandbar breaking the surface. The Earth is a perfect sphere of water, interrupted only by the occasional volcanic eruption, a black cone of basalt rising above the waves, steaming and hissing, pouring fresh lava into the sea, and even those islands are temporary. The ocean erodes them, the waves grind them down. Within a few million years, each volcanic island sinks back beneath the surface, dissolved and dispersed as if it had never been. The ocean heals itself. The surface returns to its unbroken state, water and sky and nothing else. But the ocean was not left in peace. Around 4.1 to 3.8 billion years ago, the inner solar system experienced a period of intense bombardment, the Late Heavy Bombardment, as it is sometimes called. Though the name is debated and the evidence is complex, the outer planets, Jupiter and Saturn, were shifting their orbits, and their gravitational influence sent a hail of asteroids and comets tumbling inward, toward the Sun, toward Mars, toward the Moon, toward Earth. The Moon's surface, which had begun to cool and darken, was hammered with impacts that created the great basins you can still see today. The Mare Imbrium, the Mare Serenitatis, enormous circular scars filled with dark basalt lava that welled up from the Moon's interior to fill the wounds. Earth, being larger, was hit even harder. But Earth had something the Moon did not. Earth had water, and water heals. Each impact was enormous. Some of the asteroids were hundreds of kilometers across, large enough, when they struck the ocean, to vaporize a significant fraction of the water and blast the steam back into the atmosphere. For a brief, terrible interval after each major impact, the ocean may have been partially boiled away. The surface temperature may have spiked above the boiling point, and any fragile chemistry that had begun to organize itself in the warm water near the vents may have been disrupted or destroyed. But each time, the steam condensed. Each time, the rain returned. Each time, the ocean refilled. The planet was resilient, the water always came back. And in the deep ocean, far below the reach of even the largest impacts, the hydrothermal vents continued to pump, the minerals continued to circulate, and the conditions for life continued to exist, uninterrupted, in the warm, dark places that the asteroids could not touch. Some scientists believe that the bombardment actually helped life begin by delivering organic molecules, amino acids, sugars, the building blocks of biochemistry, that had formed in the cold of interstellar space and been carried to Earth inside the bodies of comets. Others believe that the bombardment delayed the origin of life, destroying early attempts at self-replicating chemistry before they could take hold. The truth, as is so often the case in deep time, is that we do not know. The evidence is buried under billions of years of subsequent geology. The rocks that could tell us have been subducted, melted, reformed, erased. All we know is that by the time the bombardment ended, the ocean was still there, and life, somehow, somewhere, in some form, had begun. Let the bombardment fade. Let the asteroids stop falling. The ocean is calm again. The steam has settled. The sky is clearing slowly from a dark brown haze to the pale orange-grey that will be its colour for the next 2 billion years. And the water, the warm, dark, iron-rich water, stretches out in every direction, as far as it is possible to see, uninterrupted, unbroken, as patient as it was before the bombardment began, as patient as it will be for 1 billion years to come. This is the world for the next 1 billion years. This is the world for longer than the entire Phanerozoic, longer than the age of fish, the age of dinosaurs, the age of mammals, and the age of humans combined. A water world. A blue-green marble with no continents, no coastlines, no beaches, no cliffs, no mountains, no valleys that break the surface of the sea. Just the ocean and the sky and the slow, deep chemistry of a planet working out what it wants to become. Let yourself float on that ocean for a moment, not with effort. Just let the water hold you. It is warm. It is dark beneath you, but not frightening. The darkness is the darkness of depth, not the darkness of emptiness. Somewhere far below, the ocean floor glows faintly with the light of hydrothermal vents, cracks in the planet's skin where superheated water, 300, 400 degrees, kept liquid only by the immense pressure, shoots upward in plumes of white and black, carrying dissolved minerals that precipitate out of solution as they hit the colder water above, building tall chimneys of iron and sulfur and zinc that rise from the dark seafloor like the towers of a drowned city. The vents hiss, the chimneys grow, the minerals settle, and in the warm water around the vents, in the chemical gradient between the superheated fluid and the cold ocean, something is happening that will change the universe. Life is beginning. We do not know exactly when. We do not know exactly where. We do not know exactly how, but we know that by about 3.8 billion years ago, and possibly earlier, the first living things existed on Earth. Not plants, not animals, not even cells as you would recognize them. Something simpler, something closer to a chemical reaction that had learned to copy itself. A self-replicating molecule wrapped in a membrane of fatty acids, drawing energy from the chemical gradients around the hydrothermal vents, splitting, copying, splitting again, making errors in the copying that occasionally produce something slightly different, slightly better, slightly more efficient. Evolution had begun, not as a plan, not as a direction, just as a consequence of chemistry and time and the simple, astonishing fact that some molecules, given the right conditions, can make copies of themselves. Here is a quiet mystery that is worth holding for a moment, as you lie still and breathe. The sun, when life first appeared, was about 30% dimmer than it is today. 30%. That is an enormous difference. If you took the modern Earth and dimmed the sun by 30%, the entire planet would freeze solid. The oceans would become ice, the atmosphere would collapse, and nothing would survive. And yet the Archean Earth was not frozen. It was warm. The ocean was liquid. The temperature was comfortable enough for microbes to thrive. How? This is called the faint young sun paradox, and for decades it puzzled scientists. The answer, as best we understand it, is greenhouse gases. The early atmosphere was rich in carbon dioxide and methane, far richer than the modern atmosphere, and those gases trapped enough heat to compensate for the dimmer sun. The planet kept itself warm the way you keep yourself warm under a blanket, not by generating more heat, but by preventing the heat that is already there from escaping. The methane came, in large part, from life itself. The earliest microbes, the methanogens, the archaea, that lived in the hot dark water near the vents, produced methane as a metabolic byproduct. They ate hydrogen and carbon dioxide and they exhaled methane, billions upon billions of them, in every cubic meter of the warm dark ocean, each one producing a tiny amount of methane that rose through the water column and accumulated in the atmosphere, thickening the blanket, keeping the planet warm. Life was keeping itself alive. The microbes were maintaining the conditions for their own existence, not by intention but by chemistry, the way a fire maintains the conditions for its own burning by drying out the wood around it. It was the first great feedback loop in the history of the biosphere, life producing the gas that kept the planet warm enough for life to continue producing the gas. That loop ran for over 1 billion years. It is one of the most elegant and stable systems ever to exist on this planet. A thermostat built from biology and geology and atmospheric chemistry, self-regulating, self-sustaining, requiring no maintenance and no oversight, running in the background of an empty ocean, under a dim sun on a planet that had no name and no one to notice how beautifully the whole thing worked. Let that elegance rest with you. You do not need to understand it fully. Just let the idea of it settle. A warm ocean, a dim sun, tiny invisible microbes exhaling the gas that keeps their world from freezing, a blanket made of breath, a thermostat made of life. It is enough to know that it worked, that it held, that it kept the water liquid and the chemistry running for 3 billion years, while the planet slowly, slowly did the work of building continents. The first life was invisible. You could have swum through a cloud of the earliest microbes and never known they were there. They were smaller than the smallest grain of sand, smaller than the wavelength of visible light, and they lived in a world of chemistry, not light, drawing their energy from hydrogen and sulfur and iron, not from the sun. They were anaerobic. Oxygen was poison to them, and there was no oxygen in the early ocean or the early atmosphere. They lived in the dark, in the warm, in the deep, and they were the only living things on the planet for hundreds of millions of years. Try to hold the strangeness of that. For hundreds of millions of years, a span of time longer than the entire age of dinosaurs, longer than the entire age of mammals, the only living things on Earth were single-celled organisms that you could not see without a microscope, living in hot, dark water, eating chemicals, reproducing by splitting in half, evolving so slowly that 1 billion years of change would not produce anything visible to the naked eye. No movement, no sound, no colour, no shape that you would recognize as alive, just chemistry, endlessly complicated, endlessly inventive, endlessly patient chemistry, building the molecular toolkit that all subsequent life would inherit, the genetic code, the cell membrane, the basic machinery of metabolism, the ability to take energy from the environment and use it to build copies of yourself, These are not small inventions. These are the foundations of everything, and they were laid in the dark, in the deep, in the warm water of an ocean that had no shore, by organisms that had no eyes and no brains and no awareness that they were doing anything remarkable at all. There is a deep comfort in that, if you let yourself feel it. The most important work does not require awareness. The most fundamental processes do not require supervision. The chemistry of life ran itself for 1 billion years before anything alive was complex enough to notice that it was alive. The work happened anyway. The foundations were laid, the toolkit was built, and everything that came after, every eye, every wing, every thought, every dream, was built on that foundation, in the dark, by organisms that did not know they were building anything. But then something changed. Somewhere, somehow, a microbe developed a new trick. Instead of drawing energy from chemicals in the water, it learned to draw energy from light. Photosynthesis. Not the kind of photosynthesis that plants do today, that came later, but an earlier, simpler version, using light to split molecules of hydrogen sulfide instead of water, producing sulfur as a waste product instead of oxygen. These early photosynthesizers, oxygenic phototrophs as scientists call them, spread across the shallow waters of the global ocean, forming thin films on every surface that caught the light. They were still invisible individually, but collectively they changed the colour of the world. The shallow waters turned faintly green. The surface of volcanic rocks that poked above the waves became slippery with microbial slime. Life was no longer confined to the deep vents. It had found the sun. And then, perhaps around 2.7 billion years ago, though the dates are debated and some evidence suggests earlier, a group of microbes took the process one step further. Instead of splitting hydrogen sulfide, they learned to split water itself, ordinary water, H2O. They used the energy of sunlight to tear water molecules apart, capturing the hydrogen for their own use and releasing the oxygen as waste. These were the cyanobacteria, the blue-green algae, the tiny single-celled organisms that would, over the course of the next several 100 million years, completely transform the chemistry of the ocean, the atmosphere, and the planet. The oxygen they produced did not immediately fill the atmosphere. For hundreds of millions of years, the oxygen was absorbed, soaked up by the dissolved iron in the ocean, which reacted with the oxygen to form iron oxide. Rust. The ocean literally rusted. Layer by layer, the iron precipitated out of the seawater and settled on the ocean floor, forming the banded iron formations that geologists find today in the oldest rocks on Earth. Alternating bands of red and silver grey, each band representing millions of years of slow, patient chemistry, each band recording the quiet war between the oxygen the cyanobacteria were producing and the iron the ocean was using to absorb it. Imagine those bands forming. Imagine sinking slowly through the warm green water of the Archean Ocean, down through the photic zone where the cyanobacteria drift in their billions, tiny, invisible, each one a factory of oxygen, down through the darker water where the dissolved iron turns the ocean the colour of weak tea, down to the seafloor where the rust is settling, a fine, soft, red-brown sediment drifting down like snow in a very slow and very quiet winter. It falls for millions of years, it builds up in layers, it compresses, it hardens, and it records, in its alternating colours, the slow transformation of a planet from one kind of world into another. Breathe slowly. Let the image of the falling rust settle in your mind like the sediment itself. There is no hurry. The banded iron formations took 2 billion years to form. You have all night. The ocean at this time, the Mesoarchean, roughly 3.2 to 2.8 billion years ago, was a world of astonishing chemical richness, even though it was biologically simple. The water was stratified into layers, each with its own chemistry, its own temperature, its own population of microbes. Near the surface, in the sunlit zone, the cyanobacteria and the anoxygenic phototrophs drifted in vast invisible clouds, capturing light, producing organic matter, releasing tiny amounts of oxygen that were immediately consumed by the iron dissolved in the water around them. Below the sunlit zone, in the dim twilight water, chemotrophic microbes fed on the organic matter that drifted down from above. Decomposers, recyclers, the first scavengers, breaking dead microbial cells back into their constituent molecules and returning nutrients to the water column. Deeper still, In the total darkness of the abyss, the archaea and the methanogens clung to the seafloor near the hydrothermal vents, eating hydrogen and sulfur and carbon dioxide, exhaling methane, living in a world of perpetual night and perpetual warmth, utterly indifferent to what was happening thousands of meters above them in the sunlight. Each layer was a world unto itself. Each layer had its own ecology, its own food web, its own chemical signature, and together they formed a system, the first true ecosystem on Earth, a vertical column of interdependent life stretching from the seafloor to the surface, cycling carbon and nitrogen and sulfur and iron through a web of metabolic reactions that was, in its way, as complex and as beautiful as any tropical rainforest. You could not see it. You could not smell it. If you had been floating on the surface, you would have seen nothing but dark water and an empty sky. But beneath you, in every drop of that warm ancient ocean, the machinery of life was running, quietly, efficiently, without supervision, without purpose, simply because the chemistry allowed it and the energy was there. There is a lesson in that, perhaps, for the moments before sleep. The most important things are often invisible. The most transformative processes are often silent. The work that matters most, the work of growth, of healing, of restoration, happens in the dark, in the quiet, without fanfare. Your body is doing it right now. As your breathing slows and your muscles relax, your cells are repairing themselves, sorting their chemistry, clearing the metabolic debris of the day. You do not need to supervise this process. You do not need to understand it. You only need to let it happen, the way the Archean Ocean let its chemistry happen, patiently, in the dark, trusting the process because the process has been working for a very long time. The tides of the Archean Ocean were still stronger than modern tides. The moon, though much further away than it had been in the Hadean, was still considerably closer than it is today, and the tidal bulge it raised on the ocean surface was perhaps twice the height of modern tides. In the shallow waters around the scattered volcanic islands, these tides created a constantly shifting landscape of exposed rock and flooded pools, what geologists call a tidal flat, a zone where the boundary between ocean and land is not a line but a gradient, a slow transition from permanently submerged to occasionally exposed to permanently dry. These tidal flats, where they existed, were extraordinarily important for the chemistry of early life. The repeated wetting and drying concentrated dissolved chemicals, evaporating the water and leaving behind crusts of salt and mineral that were redissolved on the next tide. This cycle of concentration and dilution, repeated billions of times, may have been crucial for the assembly of complex organic molecules, the amino acids, the nucleotides, the fatty acids that are the building blocks of life as we know it. The tides, in other words, were not just a physical phenomenon. They were a chemical engine, driven by the moon, powered by gravity, running on the patient interaction of water and rock, and the slow retreat of the moon through the sky. Now. While the cyanobacteria were slowly oxygenating the ocean, something else was happening deep inside the Earth. Something that would eventually answer the question that is at the heart of this story. Where did the continents come from? To understand this, you need to know one thing about rock. Not all rock is the same density. The basalt that forms the ocean floor, dark, dense, heavy with iron and magnesium, is heavier than granite. Granite, lighter in colour, lighter in weight, rich in silicon and aluminium and oxygen, is the stuff that continents are made of. And the question of where continents come from is really the question of where granite comes from, because granite does not form easily. It does not simply crystallize out of magma the way basalt does. It requires a more complicated process, a process that, as it turns out, requires the ocean itself. Here is how it works, in the simplest terms. The Earth's interior is hot. It is hot enough to keep rock in a state that is not quite liquid and not quite solid. A slow, thick, plastic flow, like honey that has been left in a cold room. This hot rock rises in some places and sinks in others, creating enormous convection cells that churn slowly through the mantle over millions of years. Where hot rock rises to the surface, it melts and forms new oceanic crust, dark basalt, spreading outward from mid-ocean ridges like a slow conveyor belt. Where old oceanic crust is pushed back down into the mantle, at subduction zones, it sinks, carrying with it water that has been trapped in its minerals by millions of years of sitting at the bottom of the ocean. And this is the crucial part. When that wet basalt sinks into the hot mantle, the water lowers the melting point of the surrounding rock. Partial melting occurs, and the melt that forms is not basalt. It is something lighter, something richer in silicon, something closer to granite. This lighter melt rises because it is less dense than the rock around it, and it accumulates near the surface, forming patches of lighter crust that are too buoyant to be subducted. They float, they persist, they grow, slowly as more and more light material is added from below. They become, over hundreds of millions of years, continents. The earliest evidence of continental crust dates to about 4.4 billion years ago. Tiny crystals of a mineral called zircon, found in younger rocks in the Jack Hills of Western Australia, that preserve chemical signatures of water and granite from the Hadean eon. These zircons are the oldest known fragments of Earth's crust. They are smaller than grains of sand, and they tell us that even in the age of fire, even when the surface was still a magma ocean, the process of continent building had already begun. Deep inside the Earth, in the hot dark places where chemistry and physics and the simple patient mechanics of density sorting were already separating the light from the heavy, the buoyant from the dense, the future continent from the future ocean floor. But the zircons are fragments, isolated crystals in younger rock, the first actual land masses, coherent bodies of continental crust large enough to rise above sea level and stay there, did not appear until much later. The oldest known craton, a stable block of continental crust, is the Pilbara Craton in Western Australia, parts of which date to about 3.6 billion years ago. The Karpval Craton in southern Africa is of similar age. These were not continents in the modern sense. They were small, perhaps the size of Iceland or Madagascar, and they were alone, surrounded on all sides by the global ocean, two small grey-pink rafts of granite floating on a dark sea of basalt. Imagine them. Imagine sailing across the Archean Ocean, warm, dark, green-tinged, the sky a hazy orange-grey, and seeing for the first time something that is not water. A low grey shoreline barely rising above the waves. No trees, no grass, no soil, just bare granite pitted by rain, cracked by heat and cold, streaked with pale veins of quartz. The waves break against it with a sound that is almost familiar, the hiss and sigh of water on stone. But the stone is like no stone you have ever seen. It is new. It is the newest thing on the surface of the planet. It is the first land. Stand on it if you like. Feel the warmth of it beneath your feet. It is still warm, heated from below by the mantle, heated from above by the dim white sun. The rock is rough. There is no sand, because sand is what happens when rock is broken down by weather and life over millions of years, and this rock has not been here long enough for that. There is no soil. There are no tide pools. There are no shells. There is nothing alive on this land at all. Life is still in the ocean, still microscopic, still billions of years away from crawling onto shore. You are standing on the first continent, and it is the most barren, most empty, most profoundly lonely landscape you have ever seen. And it is beautiful, not in the way a garden is beautiful or a sunset or a face. Beautiful in the way that emptiness is beautiful. The beauty of pure potential, of a blank page, of a world that has not yet decided what it wants to become. Let that feeling rest, the loneliness of the first land, the patience of the first rock. You are standing on the future. Everything that will ever grow, everything that will ever walk, everything that will ever build a fire or write a poem or fall asleep listening to a story about deep time, all of it will happen on rock like this, on granite, on the light stuff that floated to the top. The Jack Hill zircons deserve a moment of quiet attention. They are found in Western Australia in a formation of younger rock called a conglomerate, a jumble of pebbles and sand cemented together about 3 billion years ago. But within that conglomerate, scattered like raisins in a fruitcake, are tiny crystals of zircon, zirconium silicate, one of the hardest and most durable minerals on Earth, virtually indestructible by heat, pressure, or chemical weathering. These crystals survived everything: the subduction of the crust they formed in, the melting of the rock around them, the erosion and redeposition and burial and uplift that followed. They are time capsules. They are messages from the Hadean, delivered through 3 billion years of geological chaos, still legible, still carrying the chemical fingerprints of the world in which they formed, and what those fingerprints tell us is extraordinary. The oxygen isotope ratios in the oldest Jack Hill zircons, crystals dated to 4.4 billion years ago, indicate that they formed in the presence of liquid water. Not steam, not ice, liquid water. This means that by 4.4 billion years ago, barely 100 million years after the moon-forming impact, the surface of the Earth had cooled enough for water to exist in liquid form. The rain had begun, the ocean was forming, and somewhere, in the margins of that earliest ocean, the first thin slivers of continental crust were already crystallizing, not yet large enough to rise above the surface, not yet coherent enough to be called land, but there. Present. Beginning. The tiny zircon crystals are the proof. They are the oldest surviving witnesses to the birth of the ocean and the first whisper of the continents. Hold one in your mind. A crystal smaller than a grain of sand, 4.5 billion years old, carrying inside its lattice the chemical memory of the first water on Earth. It has been through everything. It has been subducted into the mantle and returned. It has been heated to the point where the rock around it melted and it did not. It has been tumbled in rivers, buried in sediment, compressed into stone, uplifted by tectonic forces, and finally exposed at the surface of the Australian desert, where a geologist picked it up and held it to the light and read, in the arrangement of its atoms, a message from the very beginning of the world. That crystal is still there. You could hold it in your palm, it would weigh almost nothing, and it would be the oldest thing you have ever touched. Older than any fossil, older than any rock formation, older than the continents themselves. It is a fragment of the Hadean, a splinter of the time before time, a tiny, almost weightless piece of evidence that the ocean, and with it, the possibility of everything that followed, began earlier than anyone had imagined. Let the zircon rest. Let it settle into the sediment of your imagination, the way it settled into the sediment of the ancient riverbed 3 billion years ago. It is not going anywhere. It has waited this long. It can wait a little longer. The cratons grew. Slowly, over hundreds of millions of years, the patches of continental crust expanded. New granite was added from below, as more oceanic crust was subducted and more partial melting occurred. Old cratons collided with each other and fused, forming larger blocks. By about 2.7 billion years ago, the Neo-Archean, there was enough continental crust on Earth to form the first supercontinent, or something close to one. Geologists call it Knorland, though the name is tentative and the evidence is fragmentary. It was not like Pangaea. It was smaller, perhaps the size of modern Africa, and its outline is largely a matter of educated guesswork. But it was a continent, a real continent, a body of land large enough to have its own weather, its own rivers, its own coastline. For the first time in Earth's history, the ocean had a shore, and on that shore something wonderful was happening. The cyanobacteria, the tiny oxygen-producing microbes that had been living in the open ocean for hundreds of millions of years, found the shallow waters around the new continent particularly hospitable. The water was warm and nutrient-rich, fed by minerals washing off the bare granite. Sunlight penetrated easily in the shallows, and in those shallows the cyanobacteria began to build structures, not deliberately, not with intention, but simply as a consequence of their growth. They formed sticky mats on the surfaces of rocks and sediment, and those mats trapped particles of sand and silt, building up in thin layers, layer upon layer, year upon year, century upon century, until they formed dome-shaped mounds that rose above the surrounding seafloor. These are stromatolites. They are the oldest visible structures built by living things on Earth. Some of the oldest known stromatolites, from the Pilbara region of Western Australia, are 3.5 billion years old. They are still forming today in a few sheltered bays in Australia and the Bahamas, looking almost exactly as they looked 3.5 billion years ago. Low, rounded, grey-green domes, rising from shallow turquoise water, warm to the touch, rough with the texture of 1,000 thin layers of microbial life. Picture a field of them, a shallow lagoon on the coast of Knorland, warm water no deeper than your waist. The bottom visible through the green-tinged clarity. Dozens of stromatolites rise from the sandy floor, each one the size of a large pillow, each one gently rounded on top, each one covered in a thin slime of living cyanobacteria. Small bubbles of oxygen rise from their surfaces and pop at the waterline. Tiny, continuous, like the bubbles in a glass of mineral water. The sound is almost inaudible, a faint, continuous fizzing. The sound of a planet being oxygenated, one bubble at a time. Stay there for a moment. Stand in that warm water. Feel it against your calves. Feel the sun, dimmer than you are used to but warm enough, on your shoulders. The air smells different here, cleaner. There is a faint sharpness to it that was not there before, a hint of something you cannot quite name. It is oxygen. Not much. The atmosphere is still less than 1% oxygen, a tiny fraction of the modern levels, but it is there. The cyanobacteria are winning their quiet war against the iron in the ocean. The rust is settling. The water is clearing. And the air, for the first time in Earth's history, contains a molecule that will one day allow animals to breathe, fires to burn, and iron to corrode. The world is changing. It is changing so slowly that nothing alive can perceive it. But it is changing. The Great Oxygenation Event, that is the name geologists give to the period around 2.4 billion years ago, when oxygen levels in the atmosphere rose sharply enough to leave a clear signal in the rock record. It was not a single event, despite the name. It was a slow accumulation, a tipping point reached after hundreds of millions of years of microbial oxygen production. The dissolved iron in the ocean had finally been used up, all of it oxidized, all of it settled to the seafloor as banded iron formations. There was nothing left to absorb the oxygen, and so the oxygen began to accumulate in the atmosphere, molecule by molecule, year by year, until it reached a level that was, for the first time, detectable. The consequences were enormous. Oxygen is a reactive gas. It destroys things. It corrodes metals. It breaks apart organic molecules that were stable in an oxygen-free world. For the vast majority of life on Earth at that time, the anaerobic microbes that had been thriving in the oxygen-free ocean for over 1 billion years, the rise of oxygen was a catastrophe, a mass extinction. The oxygen poisoned them, broke apart their enzymes, disrupted their metabolisms. They retreated to the few remaining oxygen-free environments, the deep ocean, the mud at the bottom of lakes, the interiors of rocks, where their descendants still live today, in the dark, in the quiet, unchanged for 2 billion years. But for the microbes that had evolved to tolerate oxygen, and eventually to use it, the Great Oxygenation was an opportunity. Oxygen-based metabolism is far more efficient than anaerobic metabolism. It releases far more energy per unit of food. The organisms that could use oxygen grew faster, reproduced more, colonized new environments. They were the ancestors of everything you know. Every plant, every animal, every fungus, every breath you have ever taken. The oxygen that the cyanobacteria produced and that nearly destroyed life on Earth in the process is the same oxygen that keeps you alive right now, as you lie wherever you are lying, breathing slowly, drifting towards sleep. Breathe in. Feel the oxygen enter your lungs. Feel it cross into your blood. Feel it reach your fingertips, your toes, the muscles of your eyelids. That oxygen was invented by microbes in a warm, shallow ocean on the shore of a continent that no longer exists, under a sun that was 30% dimmer than the one you know, on a planet that was still mostly water, still mostly empty, still mostly waiting. You are breathing the legacy of cyanobacteria. You are breathing the exhaust of the oldest living technology on Earth. Let that breath go. Let it carry some of the weight of the day with it. The cyanobacteria did not hurry. The oxygen accumulated over hundreds of millions of years. You do not need to hurry either. The continents are still rising, very slowly, and the story is not over. There is something else the Great Oxygenation left behind. Something visible. Something you could hold in your hand if you visited the right outcrops in Western Australia or South Africa or northern Minnesota. Banded iron formations. We mentioned them earlier. The layers of red and silver-grey sediment that accumulated on the Archean seafloor as the dissolved iron in the ocean reacted with the oxygen and precipitated out. But it is worth pausing to look at them more closely, because they are among the most beautiful rocks on Earth, and they record in their alternating bands one of the most important chemical transitions in the history of the planet. Each band is a layer of sediment. The red bands are iron oxide, hematite and magnetite, the rust of the ancient ocean, and the grey bands are silica, chert, precipitated from the seawater between the pulses of iron deposition. The bands alternate with a regularity that is almost musical. Red, grey, each one a few millimetres to a few centimetres thick, each one representing a period of time that might be years, or decades, or centuries, depending on the rate of deposition. Some geologists have speculated that the banding reflects seasonal cycles, the cyanobacteria producing more oxygen in the warmer months, oxidizing more iron, depositing a red layer, then slowing in the cooler months, allowing the silica to dominate, depositing a grey layer. Others have proposed longer cycles, fluctuations in volcanic activity, or in the upwelling of iron-rich deep water to the surface. The truth is that we do not know what caused the banding, but we know that it is real, and that it is consistent, and that it extends across entire continents, preserved in rocks that are 2.5 billion years old, as if the planet had kept a diary in 2 colours for 1 billion years and then buried it in the earth for us to find. These rocks are the source of most of the iron ore mined on Earth today. The steel in bridges, in buildings, in cars, in the device you're listening to, all of it was once dissolved in the Archean Ocean. All of it was precipitated by the oxygen that cyanobacteria exhaled. All of it settled to the seafloor in thin red layers that were compressed and buried and heated and uplifted and finally exposed at the surface of the modern Earth, where it was dug up and smelted and shaped into the structures and machines of the 21st century. The iron in your car was rusted by microbes in a warm ocean 2.5 billion years ago. The world is connected in ways that are almost too vast to comprehend. Everything comes from somewhere. Everything has a history. And the history of iron is the history of oxygen, which is the history of cyanobacteria, which is the history of photosynthesis, which is the history of light, which is the history of the sun, which is the history of the cloud of dust and gas that collapsed under its own gravity 4.5 billion years ago to form the solar system in the first place. The chain of causation stretches backward without a break, all the way to the beginning, and every link in the chain is connected to every other link, and every link is holding you up right now, in this moment, as you breathe and rest and drift. Let the chain settle. You do not need to hold it. It holds itself. It has been holding itself for 4.5 billion years. It will hold for a while longer. After the Great Oxygenation, the world entered a period of extraordinary cold. This is one of the great ironies of Earth history. The cyanobacteria, by producing oxygen, may have triggered the most severe ice age the planet has ever experienced. Here is why. Before the Great Oxygenation, the atmosphere contained large amounts of methane, a potent greenhouse gas that had been keeping the planet warm despite the dimmer sun. When oxygen rose, it reacted with the methane and destroyed it, converting it to carbon dioxide and water. Carbon dioxide is a much weaker greenhouse gas than methane. The greenhouse effect weakened, temperatures plummeted, and by about 2.3 billion years ago, the Earth was locked in a glaciation so severe that ice may have reached the equator. This is the Huronian glaciation, the first Snowball Earth event, a planetary deep freeze that lasted for perhaps 300 million years. Imagine the ocean now. Not warm, not green, not calm. Cold, grey, choked with ice. The surface of the global ocean is frozen solid in many places. Thick white ice stretching from pole to equator, cracking and groaning as it shifts, reflecting sunlight back into space and making the cold worse. The continents, still small, still bare, still made of nothing but granite and rain, are buried under glaciers kilometres thick. The sky is clear and cold and pale. The sun, still dim, hangs low and distant. It is the coldest the Earth has been since the Hadean, and it will not warm again for a very long time. But beneath the ice, the planet is still alive. The hydrothermal vents are still pumping heat into the deep ocean. The cyanobacteria, reduced in number but not eliminated, cling to the thin strips of open water near volcanic hotspots and in cracks in the ice. And the interior of the Earth is still churning, still convecting, still slowly building continental crust, oblivious to the cold at the surface. The continents do not care about ice ages. They are made of a process that happens in the mantle, thousands of kilometres below the surface, where the temperature is always hot enough to melt rock, and the concept of weather does not apply. The ice comes and goes. The continents grow. How did the Huronian glaciation end? The answer is volcanoes. Even while the surface was locked in ice, the Earth's interior continued to release carbon dioxide through volcanic eruptions, slowly, steadily, century after century. Normally, carbon dioxide is removed from the atmosphere by the weathering of rocks. Rain dissolves CO2 and carries it to the ocean as carbonate. But when the entire surface is frozen, there is no rain. There is no weathering. The carbon dioxide simply accumulates, building up in the atmosphere year after year, with no mechanism to remove it. Over millions of years, the greenhouse effect strengthened. The temperature rose, the ice began to melt, and when it melted fast, perhaps in as little as a few thousand years, because as the ice retreated, it exposed dark ocean water that absorbed more sunlight, which raised the temperature further, which melted more ice. The feedback loop ran in reverse, the snowball thawed, and the world that emerged from the ice was different from the one that had entered it. The ocean was warmer, the atmosphere was thicker, the carbon dioxide levels were hundreds of times higher than modern values, creating a greenhouse effect so intense that tropical temperatures may have reached 50 or 60 degrees Celsius. It was, for a time, a hothouse world, the opposite extreme from the snowball, as if the planet had overcorrected, swinging from one end of the thermometer to the other, in the geological equivalent of a deep, shuddering breath. But the hothouse did not last either. The exposed rock began to weather. The rain, real rain, warm rain, falling on bare granite for the first time in 300 million years, dissolved the carbon dioxide and carried it to the ocean as dissolved carbonate. The carbonate settled on the seafloor. The greenhouse effect weakened. The temperature dropped, slowly, back to something moderate, and the planet settled into a new equilibrium, warmer than the snowball, cooler than the hothouse, with open water from pole to pole, and a thin, persistent haze of carbon dioxide and methane, keeping things comfortable enough for the microbes that had survived the cold to flourish once more. The stromatolites returned to the shallow waters in enormous numbers. The banded iron formations resumed their slow accumulation on the seafloor, and the cyanobacteria, undaunted, continued their patient work of oxygenation, exhaling their tiny bubbles into an atmosphere that was now, finally, able to hold them. The worst was over. The planet had survived its first great crisis, and the crisis, in a way that no one could have predicted, had made the planet stronger. The high carbon dioxide levels during the thaw had accelerated the weathering of continental rock, which had accelerated the formation of new minerals, which had accelerated the delivery of nutrients to the ocean, which had fed the microbes, which had produced more oxygen. The Huronian glaciation, for all its severity, was not a setback. It was a step. A painful, frozen, 300 million year step, but a step nonetheless in the slow construction of a habitable world. Let the cold of the glaciation fade from your mind. Let the warmth return. The ocean is open again, the sky is clearing, the volcanoes are steaming on the horizon, and the rain is falling, soft and warm, on the bare granite cratons that dot the surface of the slowly changing planet. And grow they did. By about 2 billion years ago, after the Huronian glaciation had ended and the climate had stabilized, the Earth's continental crust had expanded dramatically. The small cratons of the Archean, Pilbara, Kapval, and a handful of others, had collided and merged, forming a true supercontinent. Geologists call it Columbia, or sometimes Nuna. It was large, perhaps as large as all the modern continents combined, and it occupied a broad belt across the equatorial region of the planet. For the first time, there was more land than just scattered islands. For the first time, the ocean had a coastline that stretched for tens of thousands of kilometers. For the first time, the rain that fell on the interior of the continent had to travel vast distances before it reached the sea, carving rivers, filling lakes, weathering the granite into the first soils, thin, mineral-rich, orange-red with iron, utterly devoid of life but slowly becoming hospitable. Imagine standing on the coast of Colombia. You are at the edge of the largest body of land that has ever existed on this planet up to this point. Behind you, the continent stretches inland for thousands of kilometers. Bare, flat, grey-pink granite and dark gneiss, cut by wide, shallow rivers that meander across the empty landscape like veins on the back of an old hand. The rivers carry no silt because there is no soil to erode, only rock dust, fine and gritty, the colour of rust and ash. The rivers empty into broad deltas where the fresh water meets the salt, and in those deltas the chemistry is rich, and the stromatolites are enormous. Some of them are metre-tall, dome-shaped towers of microbial life rising from the shallow water like the stumps of trees in a flooded forest. They are the largest structures on the planet. They are built by organisms too small to see. The coast itself is unlike any modern coastline. There are no beaches, because beaches require sand, and sand requires the long grinding work of waves on rock and coral and shell, and there is no coral and no shell. Those will not exist for another billion years. Instead, the coastline is bare rock, grey granite sloping gently into the warm dark water, smoothed by the tides, darkened by thin films of microbial growth that cling to every surface below the waterline. The waves are small here, in the sheltered bays, and they make a soft, repetitive sound as they lap against the stone. A sound that is not quite like any modern wave, because the water is different, the rock is different, the air is different, but the rhythm is the same. The rhythm of water meeting stone is the same. It has always been the same. Stand there for a moment. Feel the warm rock beneath your feet. Feel the spray of the small waves on your ankles. The water is warm, not as warm as the Archean Ocean, but still well above modern tropical temperatures, perhaps 35 or 40 degrees. The air is warm too, and thick and slightly hazy. The sun is bright enough now to make you squint. It has brightened by about 10% since the beginning of the story, and though it is still dimmer than the modern sun, it is closer to what you know. The shadows it casts are sharper, the colours it illuminates are clearer, and the sky above you, for the first time since the Earth was formed, is showing traces of a colour that no eye has ever seen on this planet before. The sky had changed too. The oxygen levels, though still far below modern values, had risen enough to create a thin ozone layer in the upper atmosphere. Ozone, a molecule of 3 oxygen atoms, absorbs ultraviolet light, and for the first time, the surface of the land was partially shielded from the sun's most damaging radiation. The sky was beginning to turn blue, not the deep rich blue of a modern summer day, but a pale, washed-out blue, the blue of a watercolour painting where the artist has used too much water and not enough pigment. But blue, the first blue sky, and beneath it, the first continent, bare and warm and waiting. It is tempting to rush forward from here, to skip ahead to the Cambrian explosion, to the first fish, to the first plants on land, to the dinosaurs and the mammals and the humans. But the story tonight is not about what came after. It is about the waiting. It is about the 3 billion years of patience that preceded everything you think of as the history of life. 3 billion years of ocean. 3 billion years of chemistry. 3 billion years of the planet sorting itself out layer by layer, density by density, until the light rock floated to the top and the heavy rock sank to the bottom, and the water found its level and the continents appeared, not with drama, not with fanfare, but with the slow, quiet certainty of something that was always going to happen, given enough time. The Earth is a patient planet. It does not hurry. It does not worry. It has no deadlines and no appointments. It simply does what physics and chemistry dictate, in the order that physics and chemistry dictate, at the pace that physics and chemistry allow. The continents were always coming. The oxygen was always coming. The blue sky was always coming. They just needed time, an enormous, almost incomprehensible amount of time, and the Earth had it. The Earth always has it. There is something comforting in that, if you let yourself feel it. The idea that the planet you live on spent 3 billion years doing nothing visible, just water, just rock, just the slow accumulation of chemistry beneath an empty sky, and that all of it was necessary. All of it was preparation. The continents could not appear until the mantle had processed enough oceanic crust. The oxygen could not accumulate until the iron had been used up. The blue sky could not form until the ozone had built up. Each step depended on the one before it, and each step took hundreds of millions of years, and none of them could be skipped or accelerated. The planet was not lazy. It was not lost. It was simply doing the slow, invisible, foundational work that had to be done before anything more complex could begin. That sounds perhaps a little like the work of falling asleep. The body does not fall asleep in an instant. It does not flip a switch. It goes through stages. The breathing slows, the muscles relax, the thoughts soften and blur, the eyelids grow heavy. The world at the edge of your senses becomes distant and warm and unclear. Each stage is necessary. Each stage prepares for the next, and the process cannot be rushed. You cannot force yourself to sleep any more than the Earth could force itself to grow continents. You can only create the conditions, the warmth, the dark, the quiet, the slow breathing, and let the process happen at its own pace, in its own time, in its own deep and patient way. So let it happen. Let the continents rise in their own time. Let the oxygen accumulate in its own time. Let your breathing slow in its own time. The ocean is still there, beneath the first thin continents, vast and dark and warm. The cyanobacteria are still there, in their shallow lagoons, fizzing their tiny bubbles of oxygen into a sky that is slowly, slowly turning blue. The stromatolites are still there, growing their patient layers, one thin film of life per year, recording the passage of deep time in a language of sediment and slime. Everything is still there. Everything is still working. And the night, like the Archean Ocean, is wide and dark and has no edge. By about 1.8 billion years ago, the supercontinent Columbia had begun to break apart. This is what supercontinents do. They form, they endure for a few 100 million years, and then the heat building up beneath them causes the mantle to crack the continent apart, spreading the pieces across the globe like fragments of a broken plate. The pieces of Columbia drifted. Some moved north, some moved south. They rotated, collided with other fragments, broke apart again. The ocean rushed into the gaps between them, forming new seaways, new coastlines, new shallow shelves where life could flourish in the sunlit water. And life was flourishing in its quiet, microscopic way. By 1.8 billion years ago, the first eukaryotic cells had appeared. Cells with a nucleus, cells with internal compartments, cells that were larger and more complex than anything that had existed before. The origin of the eukaryotic cell is one of the great mysteries of biology. It appears to have involved one microbe swallowing another and keeping it alive inside itself, a partnership that eventually became permanent. The swallowed microbe became the mitochondrion, the energy-producing organelle that exists inside almost every cell in your body right now. Your cells are chimeras. They are partnerships between two organisms that merged nearly 2 billion years ago, in the warm, dark water of an ocean that no longer exists, on a planet that was still more water than land. Think about what this means. Somewhere in the warm, dark water of the Paleoproterozoic Ocean, roughly 1.8 to 2.0 billion years ago, a large single-celled organism, perhaps an archaeon, perhaps something else, engulfed a smaller bacterium. This happened constantly in the microbial world. Larger cells swallowed smaller cells all the time, digesting them for energy and nutrients. It was the most ordinary thing in the world, except that this time, the smaller cell was not digested. It survived. It continued to function inside the larger cell, metabolizing oxygen, producing energy, living as a captive but not as food. Perhaps the larger cell could not digest it. Perhaps the smaller cell was resistant to the digestive enzymes. Perhaps by pure chance the arrangement was beneficial to both. The smaller cell received shelter and a steady supply of nutrients. The larger cell received a constant flow of energy. Whatever the reason, the partnership held. The smaller cell reproduced inside the larger cell. The larger cell reproduced, passing copies of its internal guests to its daughter cells. Over generations, over thousands of generations, over millions of years, the partnership deepened. The guest cell lost some of its own genes, transferring them to the host cell's DNA, becoming more dependent, more integrated, more permanent. It could no longer survive on its own. It had become an organelle, a mitochondrion. This event, this single, improbable, unrepeatable act of cellular swallowing, may be the most consequential event in the history of life on Earth after the origin of life itself. Without mitochondria, eukaryotic cells could not produce enough energy to grow large, to develop internal complexity, to specialize into different cell types, to form multicellular organisms. Without mitochondria, there would be no animals, no plants, no fungi, no you. The entire visible biosphere, every creature you have ever seen, every tree, every mushroom, every insect, is a consequence of one cell failing to digest another cell in a warm ocean almost 2 billion years ago. Let that thought dissolve into the darkness behind your eyes. You are a partnership. You are a collaboration between organisms that found each other in the deep past and decided, or rather, were compelled by chemistry to decide, that they were better together than apart. The mitochondria in your cells are still in a sense separate organisms. They have their own DNA. They reproduce on their own schedule. They are the descendants of free-living bacteria that gave up their independence nearly 2 billion years ago in exchange for shelter and a steady supply of food. They are the oldest tenants in the oldest building on Earth. And they are inside you right now, in every cell, in every tissue, keeping you alive with the energy they produce as you lie still and breathe and drift. The breakup of Columbia is a story told in drifting fragments. Picture the supercontinent as a single vast landmass, grey and bare, yes, but enormous, stretching across the equator like a belt around the planet's waist. Now picture it cracking, not all at once, but in stages. A rift opening along a line of volcanic activity, the crust thinning, the mantle rising beneath, magma pouring into the gap. The rift widens, water rushes in. What was once the interior of a continent becomes a narrow sea, then a wide sea, then an ocean. The two halves drift apart, carried by the slow conveyor of mantle convection, each one trailing a fringe of new oceanic crust behind it. This is how oceans are born. This is how the Atlantic Ocean formed 200 million years ago when Pangaea broke apart. And this is how the oceans of the Mesoproterozoic formed 1.8 billion years ago when Columbia did the same. The fragments of Columbia drifted across the globe for several 100 million years, some of them rotating, some colliding, some breaking apart further into smaller pieces. The geology of this period is fragmentary and difficult to reconstruct. The rocks are old, they have been buried and heated and folded and eroded and buried again, and the evidence they preserve is like a letter that has been folded and unfolded so many times that only scattered words remain legible. But geologists have pieced together enough to know that by about 1.3 billion years ago, the fragments had begun to reassemble, drawn together by the slow converging currents of the mantle, forming a new supercontinent, Rodinia. The cycle was beginning again, the same cycle that has repeated at least 5 times in Earth's history. Assembly, stability, breakup, dispersal, reassembly, a slow pulse, a heartbeat, with a period of roughly 500 to 700 million years. The planet breathes in, gathering its continents. The planet breathes out, scattering them. The ocean fills the spaces between. The ocean always fills the spaces between. Let that rhythm match your own breathing if it helps. Slow, deep, gathering and releasing. The continents gather, your lungs fill. The continents scatter, your lungs empty. The cycle repeats. It has been repeating for 3 billion years. It will repeat for another billion at least before the sun grows bright enough to boil the oceans and end the cycle for good. But that is a very long time from now. Tonight, the cycle is running smoothly. The continents are drifting. The ocean is open, and you are warm and still and held by gravity against a surface that is, itself, a fragment of the oldest continental crust on the planet. The Mesoproterozoic, the era between 1.6 and 1.0 billion years ago, is sometimes called the boring billion. It is an unfair name. Nothing that lasts a billion years is boring. But the name reflects a genuine observation. Compared to the dramatic changes that came before, the origin of life, the great oxygenation, the Huronian glaciation, and the dramatic changes that would come after, the Neoproterozoic Snowball Earths, the Ediacaran fauna, the Cambrian explosion. The boring billion was a period of relative stability. Oxygen levels held steady at perhaps 1 to 10% of modern values. The climate was warm and stable. The continents drifted and reassembled at their usual pace, and life, though it continued to evolve, slowly, incrementally, producing new varieties of single-celled organisms, did not produce anything dramatically new. No animals, no plants, no fungi, just microbes, endlessly varied, endlessly industrious, endlessly patient, going about their chemical business in the sunlit surface waters and the dark anaerobic depths, cycling carbon and nitrogen and sulfur through the same metabolic pathways they had been using for 1 billion years already. The boring billion was, in a sense, the planet resting, gathering its strength, doing the slow, invisible work of building up the conditions, the oxygen levels, the nutrient cycles, the geological complexity, that would eventually allow the explosion of complex life that was still 500 million years in the future. It was the geological equivalent of the long quiet hours before dawn, when the sky is dark and nothing seems to be happening, but the earth is turning and the horizon is slowly, imperceptibly beginning to lighten. You may be in your own boring billion right now, that long, quiet stretch of the evening when the day's activity has ended and sleep has not yet arrived, and the minutes pass slowly and nothing seems to be happening, and the mind drifts. That is not wasted time. That is preparation. That is the body doing its invisible chemistry, the same way the Mesoproterozoic ocean did its invisible chemistry. sorting, settling, preparing for whatever comes next. Trust the process. The planet trusted it for 1 billion years, and the result was the most spectacular explosion of life the world has ever seen. Your result will be simpler. Just sleep, just rest, just the quiet repair of a body that has been awake for too long. But the principle is the same. The preparation matters. The waiting matters. The boring parts matter most of all. The ocean at 1.5 billion years ago was a different place than the ocean at 4.3 billion years ago. It was cooler. It was clearer. The iron had been used up. The water was no longer green. In the shallows, where sunlight reached the bottom, the first multicellular algae were beginning to appear. Not plants, not yet, but sheets and filaments of cells working together, clinging to rocks in the surf zone, waving gently in the current. The deep ocean was still dark, still anaerobic in many places, still home to the ancient microbes that had been there since the beginning. But the surface, the sunlit upper layer, was alive in a way it had never been before. Photosynthetic organisms of a dozen different kinds drifted in the water column, capturing light, releasing oxygen, dying, sinking. Their organic remains drifting down to the dark seafloor in a slow, continuous rain of carbon that would, over millions of years, become the source rocks for oil and gas that humans would extract billions of years later. The continents at 1.5 billion years ago covered perhaps 30% of the Earth's surface. Close to the modern value. They were bare. They were lifeless. They were made of granite and gneiss and schist, ancient metamorphic rocks that had been heated and squeezed and folded by the slow violence of tectonic collision. Rivers carved deep valleys into the rock. Rain pooled in basins and formed lakes. The wind blew across the empty land, carrying dust and the faint mineral smell of fresh-cut stone. There were no trees to break the wind, no grass to hold the soil, no insects to hum in the air. Just rock and water and sky, and the slow, steady work of erosion, breaking the mountains down grain by grain, carrying the grains to the sea, depositing them on the continental shelves as sediment that would, in time, become sandstone and shale and limestone. The layered book of deep time, each page 1 million years, each chapter 1 billion. That book is still being written. The continents are still moving. The ocean is still circulating. The cyanobacteria are still producing oxygen. The cycle of rock, formation, erosion, deposition, burial, metamorphism, melting, formation again, is still turning, as it has been turning for more than 4 billion years. Nothing about this process has stopped. Nothing about it has paused. The planet you are lying on right now is doing exactly what it was doing 3.5 billion years ago, churning, sorting, building, dissolving, building again. The continents you live on are not permanent. They are temporary accumulations of light rock at the surface of a planet that is still, in its deep interior, a sphere of slowly churning heat. Given enough time, 1 billion years, 2 billion, the continents will break apart again, reassemble in new configurations, break apart again. The ocean will fill the gaps. The ocean always fills the gaps. But that is a story for another night. Tonight the story ends here, at the edge of the first continent, in the warm, shallow water of a Mesoproterozoic lagoon, under a sky that is finally, after 3 billion years of chemistry and patience, turning blue. The stromatolites fizz quietly in the shallows. The waves lap against the bare granite shore. The sun, still a little dimmer than the one you know, but close, getting closer, hangs in a pale blue sky dotted with high, thin clouds that look almost, but not quite, like the clouds you see from your window on a summer afternoon. The air smells clean. The wind is warm. The rock beneath your feet is solid and real, and will be here for a very long time. You've drifted a long way tonight. From the fire of the Hadean through the first rain, across the endless ocean, down to the hydrothermal vents where life began, back up to the surface where the cyanobacteria turned the sky blue, through the deep freeze of the Uranian glaciation, and finally here, to the shore of the first real continent, where land and sea meet for the first time and the planet begins to look, in the gentlest possible way, like home. 3 billion years. That is how long it took. 3 billion years of water and rock and chemistry and the slow, patient sorting of density in the planet's interior. 3 billion years of rain falling on basalt. 3 billion years of iron rusting in the sea. 3 billion years of microbes, invisible and uncountable, exhaling oxygen into an atmosphere that did not want it, that could not hold it, that eventually had no choice but to accept it and be transformed. And all of it, every drop of rain, every grain of rust, every bubble of oxygen, every crystal of granite rising from the mantle, all of it was happening while nothing seemed to be happening. The planet looked the same from space for most of those 3 billion years. A ball of water, a ball of cloud, a marble, unchanged, unmoved, unremarkable. And beneath the surface, everything was changing. Everything was being prepared. The continents were forming in the dark. The oxygen was accumulating in the deep. The chemistry of life was being refined, iteration by iteration, in warm water near cracks in the ocean floor. The future was being built, silently, invisibly, with the infinite patience of a planet that has nowhere to go and all the time in the world to get there. Let that patience be yours tonight. Let the weight of deep time press gently against you, not as a burden but as a blanket. The planet is old, the ocean is old, the rock beneath the continents is old, and all of it, every atom, every molecule, every crystal of quartz and every chain of DNA started in the same place, in the cloud of dust that became the solar system, in the collapse of gravity that became the sun, in the slow accretion of rock that became the earth. You are made of the same material as the continents. Your bones are calcium and phosphorus, minerals that were precipitated from ancient seawater. Your blood carries iron, the same iron that rusted in the Archean Ocean and settled to the seafloor as banded iron formations. Your cells run on oxygen, the oxygen that was exhaled by cyanobacteria in a warm lagoon on the shore of a continent that no longer exists. You are the ocean's latest project. You are what the water made, after 3 billion years of trying. The lagoon is quiet now. The sun has set. The sky above the first continent is dark and full of stars. More stars than you have ever seen, because the atmosphere is thinner and cleaner than it will ever be again, and the Milky Way blazes across the zenith like a river of spilled milk, bright enough to cast faint shadows on the granite shore. The stromatolites have stopped their fizzing for the night. Even cyanobacteria need darkness, need rest, need the slow repair that happens when the light stops coming and the chemistry shifts from production to maintenance. The waves are small, the wind has died, the temperature is dropping slowly, the way temperatures drop on clear nights near the sea, and the rock beneath you is giving back the heat it stored during the day, warming you from below as the air cools from above. It is a good place to sleep. It is, in fact, the oldest good place to sleep on Earth. The first solid ground, the first shore, the first place where a body could lie down on something that was not water, and feel the steadiness of rock, and the slow pulse of a planet's heartbeat through the stone. Nothing alive has slept here yet. Nothing alive will sleep here for another 1 billion years, but the place is ready. The bed is made, the blanket of stars is pulled up to the horizon, and the ocean, which has been here since the beginning, which was here before the continents and will be here after them, murmurs its slow, continuous lullaby against the shore. The oldest sound, the most patient sound, the sound that has been running without interruption for 4 billion years and will not stop tonight, or tomorrow night, or any night in the foreseeable future of this small, warm, endlessly patient planet. Sleep well. The continents will still be rising when you wake. The ocean will still be there. The cyanobacteria will resume their quiet work in the morning, exhaling oxygen into a sky that is almost but not quite the blue you know. And the story, the long, slow 3 billion year story of water becoming land and chemistry becoming life, will still be unfolding, as it always has, as it always will, at the pace of geology, at the rhythm of the tides, in the deep, warm, unhurried time of a planet that has never been in a rush and sees no reason to start now. The mystery will still be there in the morning,